Now we're going to study the relationship between a matrix M and the function that maps a vector x to m times x. Now, in one direction, it's pretty easy. Given a matrix M, we can define the function, maps x to m times x. The more interesting thing is going the other way. Given a function, can we find the matrix M such that that function maps x to m times x? In studying this relationship, we come up with this fundamental idea of linear functions. Let's go the easy direction first. We start with a matrix M. We define the function f of x to be f of x equal m times x. Now, what are the domain and codomain of this function? Well, let's say M is an R by C matrix over the field F. Then the domain of F is f to the C, because the input to the function has to have as its domain the label set of the matrix. Similarly, the output of the function is a vector with domain R. So the codomain of the function f is the field to the R. For this matrix, the function f of x equals m times x has a domain of R to the set sharp at and question mark, and the codomain is R to the A and B. So for example, given this as input, this is the output. Here's another example. Given this, define this function as this matrix times the input. Then the domain of the function is R3, the codomain is R2. And for example, it maps this input to this output. Now let's say we have a function and we want to compute a matrix M such that the function is f of x equals m times x. Okay, we know that the domain, let's say the domain is f to the A. So we know the input is an A vector. So for the product m times x to be even legal, we need the column label set of M to be the set A. Similarly, since the codomain is f to the B, we know that the output is a B vector, and so we need that the row label set of M is the set B. So we know that M must be a B by A matrix. Now, what are the entries of M? We have a function f, and let's say its domain is Fn and its codomain is Fm. We think there might be a matrix big M such that f of x is equal to m times x. How can we find out what the entries of this matrix are? Well, we start by writing this mystery matrix in terms of its columns. So let's say those columns are indicated as v1 through vn. Now we use the standard generators. Remember, the first standard generator is 1, and the rest of the entries are 0. The second is 0, and then 1, and then the rest is 0, and so on. So we combine standard generators with the linear combinations definition of matrix vector multiplication. So f of E1 is the matrix times the vector E1. And by the linear combinations definition of matrix vector multiplication, this product is just the first column, V1. Similarly, f of En is just the last column, Vn. Let's take a simple example, the function that stretches by 2 in the horizontal direction. Okay? And we assume this function is defined as a matrix vector multiplication for some matrix M, and we want to figure out what its entries are. Well, we plug in the standard generators. First standard generator is 1, 0. We plug in 1, 0. We know that point gets mapped to 2, 0 because we're stretching by 2 in the horizontal direction. Now we plug in the second standard vector, 0, 1. And we know this maps to 0, 1 because we're not doing any stretching in the vertical direction. So we know S applied to the first standard generator is 2, 0. And we know S applied to the second standard generator is 0, 1. So we take these two vectors and we build a matrix with those as its columns. That's the matrix. M, 2, 0 as its first column and 0, 1 as its second column. Let's try another example, rotation by 90 degrees. So let R be the function that rotates a point xy by 90 degrees, like this. And we assume that R can be defined by matrix vector multiplication for some matrix M, and we'll try to figure out what the entries are. Now we know that rotating the standard generator 1, 0 by 90 degrees gives us 0, 1. So the function should map the first standard generator 1, 0 to 0, 1. And we know that rotating the second standard generator 0, 1 by 90 degrees should give us minus 1, 0. So the function should map 0, 1 to minus 1, 0. Since the first standard generator maps to 0, 1 and the second standard generator maps to minus 1, 0, we build the matrix by making these its columns. And there it is. Now we consider a generalization of the previous example. This time we define R to take a point xy and rotate it by an angle of theta. And we assume, as before, that the function is defined by matrix vector multiplication for some matrix M. Now, we know that rotating the first standard generator 1, 0 by an angle of theta should give us the point cos theta sine theta. So column 1 of the matrix M should be cos theta sine theta. We know rotating the point 1, 0, the second standard generator, by an angle of theta should give us minus sine theta cos theta. So column 2 of the matrix is minus sine theta cos theta. And here's the matrix for rotating by an angle of theta. Try one more example, translation. So translation by 1, 2. Meaning we move the input 1 unit to the right and 2 units up. Assume this function is defined by matrix vector multiplication for some matrix M, and let's figure out the entries of M. We start with the point 1, 0, translate it, and we get 2, 2. So the first column would have to be 2, 2. We start with the second generator, 0, 1, and translate it, and we get 1, 3. So the second column of this matrix would have to be 1, 3. So the matrix would look like this. Here's a simple example. Consider the function from R4 to R4 defined by f of x equals x. That's just the identity function. Now let's assume that f of x equals m times x for some matrix M, and let's figure out what matrix. Well, we plug in the standard generators. F of E1 equals E1. So the first column is just E1. Similarly, f of E2 is E2, so the second column is E2. F of E3 is E3, so the third column is E3. And f of E4 equals E4, so the fourth column is E4. So the matrix looks like this. This is the identity matrix. So we see that the identity function, f of x, corresponds to an identity matrix. That's why we call it an identity matrix. Let's consider the function from Rn to Rn defined as follows. Given a vector x1 through xn, return the vector d1 x1 through dn xn. So what this function is doing is scaling in each coordinate. And the matrix corresponding to this function has the values d1 through dn going down the diagonal. This is called a diagonal matrix. All the entries off the diagonal are required to be 0. Now, a special case is where all the diagonal elements are 1. In that case, the function is the identity function, and the matrix is the identity matrix.